Okay, welcome to my session about unique identifier as primary key values. First question to you, who is using unique identifier as primary key values? Some of you. That's on one hand great, and on the other hand very, very bad. Who was already in a session or in my pre-con? Few of you? Okay, so a few words about my person. My name is Klaus Aschenbrenner. I provide with my company SQL Passion throughout Europe, SQL Server trainings and consulting services. I'm also a Microsoft Certified Master for SQL Server 2008. I have written the book Pro SQL Server 2008 Service Broker. Service Broker is an asynchronous messaging framework that Microsoft first introduced back with SQL Server 2005. With Service Broker, you are able to write message-based asynchronous database applications. You can also find further information about my person, about the services that I'm offering on my website at sqlpassion.at, where you will also find more free content, training content around SQL Server. What's our agenda for the next 90 minutes? In the first part, I want to give you an overview about clustered and non-clustered indexes, because as you will see later, when we are talking about unique identifier as primary key values, it's very, very important that we all have a basic understanding how clustered and non-clustered indexes are working in SQL Server. And we will see later why unique identifiers by default as primary key values are not so good. As you will also see, we can use them without any problems, but we have to tweak them in some way. And at the end of that talk, I also want to give you some information about scalability, and here you will also see that unique identifiers can be really, really good as primary key values. So at the first part I'm telling you they are just crazy, awful, and at the very end I'm just telling you they are great. Imagine that. Okay, let's start with clustered indexes in SQL Server. Every time when we create a primary key constraint in SQL Server creates under the hood a unique clustered index. Means a clustered index is a B-tree structure, it's a balanced tree, and SQL Server just physically pre-sorts and organizes our table data on that column where we have created our primary key constraint. For example, when we specify the primary key constraint on a column like custom ID, then we're just physically pre-sorting our data in that clustered index on that column. Custom ID means first custom ID comes for the second one, for the third one, and so on. Mainly you can think a clustered index is just a phone book. A phone book itself also is physically pre-sorted, in our case on last name and first name. And the same technique we are applying to our data when we create a clustered index or when we create a primary key constraint in SQL Server. The clustered index itself consists of the so-called leaf level. In the leaf level, we just store our data on so-called databases in SQL Server, and database is always 8 kilobyte large, and those records on those databases are just physically pre-sorted on that column on which we have created our clustered index. And above the leaf level, we have a so-called navigation structure, and with that navigation structure it is very, very easily to find a specific record in that leaf level. So for example, when you're searching for custom ID 1000, you perform a so-called seek operation, means you're just going through that navigation structure and you find that specific record. On the other hand, when you read rows, multiple rows from that clustered index, SQL Server can perform a so-called clustered index scan operation. And scan just means you read page by page, every page from that clustered index. Let's have a look on that. I create here a new database and I create a simple table. Every table or every record in that table is 400 bytes long, means we can store on one page of 8 kilobyte up to 20 records. You can also see for customer ID, I have here a unique identifier data type, and I create now a unique clustered index on that customer ID column. When you specify here the primary key constraint, SQL Server also creates you in the background a unique clustered index to enforce that logical primary key constraint. Okay? The next step, I insert 80,000 records in that table, takes around 20-25 seconds, means we have 80,000 records, 200 records on one page of 8 kilobytes, means we have around 4,000 pages in the leaf level of that clustered index. So when we read everything from that table, you can see in the execution plan we have a clustered index scan operator, means we are scanning the complete leaf level of that clustered index. And when we enable the session option statistics IO, SQL Server also tells us how many page reads we have. In our case, we have around 5,800 page reads in that leaf level. For example, when we search for a specific value where customer ID equals some unique identifier, then we have a clustered index seek operation, means we are going through that navigation structure and we find that specific record, means in that case we just have 3 logical reads because that clustered index consists of 3 levels. Our index root page, there's always only one index root page, then one intermediate level, and finally the leaf level of that clustered index. We can further retrieve more physical information about that index through the dynamic management function systemdb index physical stats. And as you can see also here, we have 3 index levels. We have our leaf level with 5,829 pages. We have an intermediate level of 27 pages and 1 index root page. So you can also see here very nicely that B-tree structure that SQL Server created for us with that clustered index. Okay? About the implications of that unique identifier value, we will talk about that later. But now I just want to give you a brief overview about clustered and non-clustered indexes in SQL Server. Okay? Questions so far? No. Let's move on. So we have created now on a table a clustered index. We can do that explicitly with the create clustered index statement. We can do it implicitly by defining a primary key constraint. In addition, we have the possibility to create non-clustered indexes in SQL Server. A non-clustered index is just a secondary index. Imagine we have a table with columns A, B, and C. We have on column A our primary key constraint defined, and on column C, like country, we want to create an additional column, an additional index. Imagine we have queries like we want to know all our customers from the United Kingdom, all our customers from Austria. Then in that case, a non-clustered index on that column, country, will improve the performance of such queries. A non-clustered index in SQL Server is again just a balanced tree, a B tree structure that we have already seen previously with our clustered index. In a non-clustered index, we again have the leaf level. In the leaf level, we have our index records. Means for every record in our table, you have one record in the leaf level of the non-clustered index, and on top of that leaf level, you have again a navigation structure. In that case, I have here just one additional level, in our case the root level, with our one and only index root page. When you access that non-clustered index, you can again scan the complete leaf level, and you can also make seek operations. The most important thing about the non-clustered index in SQL Server is that the non-clustered index doesn't contain your actual table data, because your table data itself is in the clustered index. Means the non-clustered index contains a logical pointer in the leaf level which points to the records in your clustered index. In the case of SQL Server adds the clustered key value, the column on which you have created your primary key constraint, into that leaf level. Means when you create your primary key constraint on a unique identifier value, which is 16 bytes long, very, very large, you also add that unique identifier value in every non-clustered index, at least in the leaf level. When you create a non-unique non-clustered index, which is normally the case, imagine a country column in a table. In that column, you will have non-unique values. You have multiple customers in the UK. In that case, you create a non-unique non-clustered index. And if you have created a non-unique non-clustered index, then SQL Server also adds the clustered key value into your navigation structure of that non-clustered index. Means you are polluting your complete non-clustered index with your unique identifier value. Just think about that. You have a badly performing clustered index, and because of that, you also have a badly performing non-clustered index. So one problem just leads to another problem. So the most important thing here is that the clustered key column, the column on which we have created our primary key constraint, is replicated in every non-clustered index. Just think about that. Imagine the following. We have a table with 1 million of records, and I create, for example, a clustered key on a column which is 100 bytes long, and I create on that table 15 non-clustered indexes. In that case, we have a storage size of those indexes of around 1.4 gigabytes. When we create a clustered key value which is only 4 bytes long, for example, an int identity column, an ever-increasing value, we have only a storage size of 57 megabytes. Just think about that. That's just a replication of the clustered key value in all of our non-clustered indexes on that table. So we generate here a large overhead. So we have a very, very large dependency in SQL Server because between our clustered and non-clustered indexes, because of that clustered key column, the column on which we create our primary key constraint. Means normally we should create a clustered key column which is unique, which is narrow, very, very small, like an int identity column, and which is also static, means it should not change. Because when your clustered key column changes, you also have to update your non-clustered indexes. Because the non-clustered index has the clustered key column as logical pointer. Okay? Let's have a look on that. I create here again the same table as previously, and I create again a clustered index on our first column customer ID with the data type unique identifier. And again we're inserting 80,000 rows into that table. Again, when we select everything from that table, we have our nice clustered index scan. We have our around 5,900 logical reads. In the next step, I create a non-clustered index on the column customer name. So imagine we have some queries where we're restricting on a specific customer name. In that case, SQL Server can use that non-clustered index. Means in that case, that non-clustered index has now the customer ID, our clustered key column, as a logical pointer in the leaf level. And in addition, we have created here a non-unique non-clustered index. Means when you not say create unique non-clustered index, then you create a non-unique non-clustered index. Means you can have duplicate values in that column. Normally, when we create our non-clustered indexes, it's a non-unique non-clustered index. Means in that case, we have now that primary key column, the clustered key column, also in the navigation structure of that non-clustered index. We can also see that very easily. I create here a simple helper table, and in SQL Server we have the undocumented dbcc int command, and with that command you can return for a specific database, for a specific table and a specific index ID, all the pages which are belonging to that index. In our case, I have just created one non-clustered index. All non-clustered indexes are starting with the index ID 2 and upward, means our non-clustered index here has the index ID of 2. As you can see, we have here 1236 pages, and now we just write with the insert into command all those pages in the previous helper table that I have created. Means we can query that helper table. For example, I retrieve here my one and only index root page. Every page in SQL Server has a page ID. In that case, we have a page ID of 6450. We copy that, and now we enable a specific trace flag in SQL Server, and now we are able to dump that page out. So we are able to see that specific page with the dbcc page command. This is our index root page. In our case, our index root page has 20 records. 20 index record means in the level below we have 20 index pages in the first intermediate level. And as you can see here, you have your index column, customer name. That's the clustered key, the primary key column on that table. And because you have created a non-unique, non-clustered index, SQL Server added your clustered key column into that index page your unique identifier column. You are polluting every index page with those unique identifiers. Means every index record here is 16 bytes longer because of that unique identifier value. Means your non-clustered index just gets larger. Means your index needs more space in your storage. Your index needs more space in the buffer pool, the main memory consumer in SQL Server, where SQL Server stores and caches those pages in main memory. Just think about that. That's the first big implication that we have. We just get larger non-clustered indexes. Means they are not as efficient as possible. Now we can take one child page ID, dump that page ID also out. Again, you see the same thing. You have the customer name, the key on which we have created our non-unique, non-clustered index, and again we have the unique identifier column. Let's go down to the third level. That's now the leaf level of that non-clustered index. And here again you also have your unique identifier values. Just think about that. Throughout the complete navigation structure, you have on every page in that index your unique identifier column. Means every index record on those pages is 16 bytes longer. Just think about that. Make sense? Are you already scared? Not yet.
So I have one question. So you're saying if it's a unique non-clustered index, then you only have the GUID on the leaf level?
Then you have the GUID only in the leaf level. Yes. So for example, when we recreate that index, drop existing equals on, and we create a unique one. Oops. Things are changing. This is our index root page, 7634. When we dump that out, you have only your non-clustered key column, because it's a unique non-clustered index. When you go a level down, again you have only your non-clustered key column. And finally, in the leaf level, SQL Server adds the unique identifier column as a logical pointer. But the unique non-clustered index is not really the common case, because normally you are dealing with non-unique values in that column. Means you are polluting your complete B-tree structure with that unique identifier value. Okay? Means in our case, when we look back, we have polluted now the complete non-clustered index, every index record with the additional unique identifier value. Normally, you should always create your clustered index first, and afterwards you should always add your non-clustered indexes. That's one best practice, and currently we say the best solution for a clustered key value is a 4-byte long integer value. For example, an int identity column, because it's just small, it's ever increasing. We will see later what that means. means you have no index fragmentation, no page splits in SQL Server. When you say, okay, my 4-byte integer, that's too small for me because I have more than 2 billions of records, take a big int. 8 bytes. Still a space saving of 100% compared to the 16-byte long unique identifier value. Okay? Let's talk now more about unique identifier as primary key values. The first most important thing is that the primary key is not the same as a clustered key or clustered index. The primary key is a constraint on the logical level. We just tell SQL Server with the primary key constraint that we want to enforce uniqueness in a specific column. Nothing more. And SQL Server by default enforces that uniqueness with the creation of a unique clustered index in the background. Means every time when we specify our primary key constraint, SQL Server creates in the background a unique clustered index for us. Nothing more. The primary key constraint is on the logical level, and SQL Server enforces that primary key constraint on the physical level with a unique clustered index. And we have a second option in SQL Server to enforce a primary key constraint with a unique non-clustered index. It doesn't matter if we use a clustered or non-clustered index. We just want to enforce uniqueness in a specific column. And that uniqueness can be enforced with a unique clustered index, which is the default option, or a unique non-clustered index, which is not the default option. What are the disadvantages of unique identifier values as primary keys? The problem is that they are not sequential. As I've already said, when we create a clustered index on that specific column, we are pre-sorting physically our data in the leaf level of the clustered index based on those unique identifier values. Means we have here that leaf level of our non-clustered index. Imagine we have 2 records on one index page, on one data page in the leaf level. In that case, we have all A's at the beginning, then we have the B values, we have the C values, maybe we have here D values, F values. Just pre-sorted, like in a phone book. Phone book is pre-sorted, clustered on last name, first name. And now imagine we insert a new record into that table and we generate that clustered key value, for example, with new ID. We have here a value. Let's take another one. Come on. AB. We have now a key value of AB, where we have to insert that value in our clustered index. Between AP and P. Do we have space? No. In that case, SQL Server has to perform a so-called page split. Means SQL Server allocates a new page which is physically somewhere else, and logically we are inserting that page, in our case, between the first and second page. Means that's our first page, that's our second page, that's our third, fourth, fifth, sixth page. Means when we now scan that index in the leaf level, we have random I/O, we are scanning forward. Then we are jumping to the new page, which is somewhere else, and then we are going back and scanning forward. Index fragmentation. Very, very slow on rotational storage. That's the first problem. When you use a unique identifier value as your clustered key value, you have an index fragmentation of nearly 100%, 99%, means the logical sorting order of those pages and the physical sorting order of those pages is not the same anymore. You mainly perform almost random I/O when you scan that leaf level of the clustered index. Random I/O, very, very slow on traditional rotational hard disks. So that's the first largest problem that we have here. In addition, such a page split needs a huge overhead in the transaction log. Means those pages in the leaf level are just interlinked. It's just a double linked list, nothing more. Means when you insert here a new page, you have to change those linkages. The first page has to link to the second new page, the second page has to link to the third page. In addition, when you insert a page in the leaf level, you need one additional record in the level above on that index page. Imagine that page is full. What happens? A page split, a cascading page split. One page split leads to another page split. And SQL Server has to log on the physical level in the transaction log what physical changes we have done on those pages. So for example, when you change one of those pointers in the leaf level, that's one transaction log record. And SQL Server can only commit your transaction when you have written out all your transaction log records into that transaction log. Means your insert transaction will take longer time. Imagine you have high availability technologies in use that are based on the transaction log, always on database mirroring. You're just slowing them down. Just think about that. I have already talked about the storage overhead. 16 bytes versus 4 bytes when we use an int identity column. That storage overhead is replicated in every non-clustered index, as we have already seen. And normally, you are not scanning anymore your leaf level. Normally, you should also cluster, pre-sort your table data on a column on which you are expecting range scans, where you are searching for a specific range. For example, data warehousing, fact tables, you mainly cluster them on a date column because you're doing range scans on a table, on a date column. For example, I want to retrieve all my records for a specific year. We do not really do range scans on unique identifier values. I've never ever seen a business requirement which told me, please give me back all records where the technical IT starts with A. Okay? Very simple example. A table with 1 million of records, 6 non-clustered indexes. You create your clustered key value on an int column. You have in storage overhead of 27 megabytes. When you do the same thing with a unique identifier value, you need 107 megabytes. Just 4 times the space. 4 bytes versus 16 bytes. Just think about it. Just a table with 1 million of records. Not too much. Performance. Page splits are costing you performance. These are just additional CPU instructions, CPU cycles that SQL Server needs. Very simple, create a table with an int identity column as a primary key, try to insert 100,000 records on a traditional rotational storage. It took me around 1 minute. When I'm doing the same with a unique identifier value, it took 1 minute 50 seconds. Random I/O, and they cost page splits, CPU overhead. And still, when you are running on SSDs, the page splits itself just costs you some CPU cycles. It's just more work than that SQL Server has to perform internally. Just think about that. Very simple to prove. Let's have a look on all those things. I create here a very bad table. Unique identifier, and we specify now our primary key constraint. When we do that in that case, we have already failed. I was also a developer in the past. I have also done all those crazy things. Unique identifiers are just great for developers. You can drive a DBA, database administrator, crazy with them. Okay, I've also done all those things. I insert into that table 100,000 records. Takes some time. And in the next step, we will check our index fragmentation with the dynamic management function systemdb index physical stats. And you will see that we have in the leaf level of the clustered index an index fragmentation of nearly 100%, 99.4%. Means almost every page in the leaf level is just out of order. Means your scan of the leaf level, where SQL Server normally assumes that this is sequential I/O, is just random I/O. We can also see that. I have here something else, and I show you something. I just return all the pages from that clustered index. As you can see, we have here those page pointers. The next page ID and the previous page ID in the leaf level. So the first page points to the next page with a page ID of 1023. So when we scan that clustered index in the leaf level, we have now to find page ID 1023. We have that page here, 1023. The next page ID of 1023 is 714. So we move forward. We search for 714. 714 points to 1150. We go forward. Random I/O, as you can see here, random I/O is just slow. It takes time. Okay? Just think about that. So as you can see, with a fragmentation of nearly 99%, means the logical and physical sorting order is not the same anymore. When we scan that leaf level, we just perform random I/O. Very, very slow. On the other hand, we have here a so-called internal fragmentation. By now we have covered external fragmentation, and here we have the so-called internal fragmentation. When SQL Server performs a page split, and we insert here that new value of AP that we have seen earlier, we have a problem. We generate in the leaf level of the clustered index some free space. Means we are wasting space. Again, you are wasting space in your physical storage, and you are wasting space in the buffer pool of SQL Server. Means when we scan the leaf level of that non-clustered index, we have 31% of free space that we are reading. Means your scan of the leaf level is in that case 31% more expensive, because the page splits are also leading to free space on those pages. Of course, that free space can be reused. Imagine we are inserting a value of AC. In that case, we don't need a page split. We just insert that record, because we have free space on that specific location where we have to insert that record based on our sorting order. So we are dealing with two kinds of fragmentation. We have the internal fragmentation and we have the external fragmentation. Two different problems. Both problems are costing you performance. And now we do the same thing with an int identity column as a primary key. We just do the same thing. I have the same table definition. We're just changing the data type to an int identity column. And again, we insert 100,000 records into that table. And then we check again our index fragmentation. And in that case, the index fragmentation is almost at 0%. Means your scan in the leaf level is just sequential I/O, one page after the another one, very, very fast. As you can see, with an index fragmentation of 1.something%, almost nothing. Again, we can see that when we go up to the dbcc int command. You can see we have here a page ID of 150, 150 points to 156, 156 to 162, 62 to 66, 66 to 178. Those are just increasing page IDs. It's just sequential I/O when you are reading. Just think about that. Very, very fast. We do not need to jump forward and backward on our physical storage when we read those pages. We just read once forward, nothing more. Very, very fast. And because we just used an int identity column for that table, you can also see that our int identity column table is smaller. We have only 2 levels, because you only deal with a 4-byte value versus a 16-byte value. Means your clustered index is just smaller. Imagine when we're reading from that table. The complete scan of the leaf level on the integer table costs you 568 page reads. When we scan our unique identifier table, it costs you 1,000 page reads. Same amount of records, 100,000 records. Because of that internal fragmentation. We are scanning around 30% of free space. Useless information, just free space. Just think about that. And you can see here on the integer table, our internal fragmentation is at 99.9%. SQL Server tries to write as many records as possible into those pages. Makes sense? We have an ever-increasing value, means we're just appending records at the very end of that table. Very simple. We just allocated the very end of our table a new page and we insert the value 1 and 2. Then we allocate another page, insert the value 3, 4, 5, 6. We are not wasting any space anymore. Therefore, the recommendation from previously, an ever-increasing clustered key value. You just insert at the very end of your clustered index, means you are not wasting any space anymore. Make sense? Are you already depressed?
Yes, I'm definitely never going to use it as a...
Sorry?
I'm definitely never going to use GUID as a clustered index.
Yeah?
What if you inherit a system that uses it?
Hopefully that hasn't.
I have.
You didn't say at the beginning it was going to get better.
Yeah.
It's like watching a film being told it's got a happy ending.
In some specific cases. Very important. Questions so far? So you can see already we have a huge amount of different problems. Just by creating a primary key constraint on a unique identifier column. I can also show you the overhead of page splits in the transaction log. I created here a simple table and I have inserted here into that table 6 records. We have here an integer column on which I have created later my clustered index, and every record is around 1000 bytes long, means we can store 8 records on a page of 8 kilobytes. As you can see here, we have inserted 1, 2, 3, 4, 6, and 7. Value 5 is missing. I insert at the very end of that index the clustered key value of 8. Means we just add at the very end of that index without any page splits that record. When we go to system to run database transactions, we can see how much space that transaction uses in the transaction log. 1256 bytes. Now we have on that page 8 records of 1000 bytes, means our page is now full. And now we insert a record in the middle of that page. Value of 5. In that case, SQL Server has to perform a page split. And guess what? The page split is very, very expensive. 7,500 bytes versus 1,200 bytes. Just think about that. You are writing more information to the transaction log, means it takes longer and it will take more time until SQL Server can commit your transaction. Okay? Another side effect of page splits. Another example where I demonstrate a cascading page split. Means we make a page split in the leaf level. Afterwards we insert a record in the level above. The page in the level above is full. Means we also need an additional page split. So one page split leads to another page split in that clustered index. I begin here, normal insert, no page split. We need here 356 bytes in the transaction log. Another transaction with a page split, 6,700 bytes. Imagine that, 300 bytes versus 6,000 bytes. 20 times more overhead in the transaction log for a cascading batch split. Just think about that. Of course, a cascading batch split is not happening always, but the traditional batch split just happens every time when we insert records randomly into that clustered index. So you're just hammering your transaction log. Means your transactions are just taking longer. Okay? So the question is now, what can we do? As we have seen, we have a huge amount of problems, and of course we want to solve those problems somehow. Of course, when we start from scratch, it's easy. Use an int identity column, or as we will see later, we can also enforce the primary key constraint with a unique non-clustered index, and we can cluster, physically pre-sort our table on a different column. When we have an existing database where we see that we have a huge amount of page splits because of the unique identifier, we have two different options. The first option is the so-called fill factor. With the fill factor, we can specify how much free space SQL Server leaves on the pages in the leaf level when we create the clustered index or when we rebuild the clustered index. Imagine the following. We have again the leaf level of our clustered index. And let's say we specify a fill factor of 50%. 50% is only good here for demonstration. As you will see in a few minutes, never ever do it on a real database. When we create that index with a fill factor of 50%, it means that SQL Server leaves 50% of our index pages free. Means we have here a value of A, first record, second record on that page, free space because of the fill factor. Then we have here a value of AC, BA, CA, DF. Means when you create a table with a fill factor of 50%, it would mean that your scan in the leaf level costs you 200% because you are scanning 50% of free space. And now think what happens when we want to insert a new value of AB into that index. What do we do? Correct, nothing. We just insert that value because we have free space. Means we can decrease with the fill factor the page splits without changing anything. It's just the option on an index. Of course, SQL Server only maintains that fill factor when we create or rebuild our index. Doesn't make sense to make always sure to leave here 50%. Of course, at some point in time, we have inserted records into that index. And then our leaf level is full. When you want to insert another new value, let's say AT, or let's make AP, then again you are causing page splits. Means you have again to rebuild your clustered index to make again free space so that you can eliminate your page splits. Okay, but just a transparent option, we don't need to change anything. 50%, as I've said, just for demonstration, it's easier. Normally, you will start with a fill factor, let's say 90–95%. You monitor your workload, you monitor your SQL Server, and you check how your SQL Server reacts. Never ever start with 50%. That's just a crazy idea. You just gradually lowering down your fill factor. Also depends on your workload, how often you are inserting, deleting, changing records in that index. That's the first option, completely transparent. Second option is that we also can enforce the primary key constraint with a non-clustered index. We can do that during the table definition, as we will see later, and we are fine. If you want to enforce the primary key constraint with a non-clustered index for an existing database, it's just pain in the, They are recording, so I'm not allowed to say that word, which starts with A and ends with SS. The problem is, when we want to enforce the primary key constraint with a non-clustered index, we have to drop our primary key constraint. Means we're losing our referential integrity. You also have to drop your foreign key constraints. Normally, I'm talking to DBAs and telling them how bad developers are. Normally, I'm saying at that point in time, we are not trusting our developers. So maybe their applications are violating the referential integrity, and therefore we just take our database offline. Means that we are the one and only user. Because when you have dropped your primary key constraint for foreign key constraints, you have no referential integrity anymore. Means when you have a badly written application, of course from someone else, that application violates your referential integrity, and afterwards you want to recreate your primary key constraints and your foreign key constraints, it doesn't work anymore. So here it really depends if you are trusting that application or not. Okay? Therefore, normally we recommend to take the database offline so that you are the one and only user that makes that change. Let's have a look on both things. So, fill factor. Again, whoops, let's drop that database in the first step so that we start from scratch. And again, I'm just starting with a bad table definition. Again, unique identifier, and we have defined the primary key constraint on that column. I insert again 50,000 records into that table. When we check again the fragmentation, you can see we have a fragmentation of nearly 100%, and in the leaf level we have 522 pages, and we have an internal fragmentation of 68%. When we make a scan of that leaf level, you can see that that scan costs us those 526 logical reads. When we insert into that table and we go to performance monitor of the Windows OS, we have also a performance counter with which we can track our page splits. We have here some access methods, and within the access methods we have page splits per second. Never ever use that performance counter. I will show you later why. I insert here 10,000 rows, and as you can see we have here now page splits. The crazy thing about that performance counter is that that performance counter will also show you page splits on an ever increasing column like an int identity column. Because in SQL Server we have two kinds of page splits, bad ones and good ones. A bad one is in the middle of the leaf level of the clustered index, and the good one is on the very end. So when you have an ever increasing value like an int identity column and you insert at the very end of your clustered index records, you still have page splits with that performance monitor, but good ones. But you're not able to tell that from that output. So that performance counter is just useless. It tells you nothing. Okay? When we look again into that clustered index, you can see now we have 618 pages. Means again, when we run a scan from that table, the scan costs us 623 logical reads. And what we do now, we just rebuild our index and we lower the fill factor. As I've already said, 50% is a crazy idea. Just good for demonstration. You can see now we have around 620 pages, and we have already 32% of free space in the leaf level of the clustered index. Means when we now rebuild our clustered index with a fill factor of 50%, we are not getting the double amount of pages, because SQL Server just increases 22%, so 18%, so that we are going down to 50%. Okay? So let's grab the name of the clustered key and rebuild that clustered index with the fill factor of 50%. When we now scan our table again, guess what? The scan costs you more, 850 logical reads, because now you are scanning 50% of free space. Just think about that. As you can see, when we go again to systemdb index physical stats, we have now an index fragmentation of 0%. Of course, we have rebuilt that clustered index. We have a page count of 845, and we have the fill factor of 50%. Means when we now insert rows into that index, we have no page splits anymore because we have free space. Just think about that. No page splits. Because with the lowering down of the fill factor, we have gained free space. As you can see, we still have a fragmentation of 0%, which is great. We have an internal fragmentation of around 60%. So SQL Server only maintains the fill factor during an index creation or index rebuild. Doesn't make sense to guarantee that fill factor forever. Why we should have always 50% free space. Means when we now insert around 40,000 records and we're lucky, we should see at the very end of that insert some page splits occurring, because now our index is again full And SQL Server needs page split so that we get free space. Means, when we check again our index fragmentation, you can see we have already a fragmentation of 24%. So around 1/4 of those pages in the leaf level are just out of order, physically. We still have the logical sorting order, but the physical sorting order is completely something else. Okay? Means that's the point in time when you see that your page splits are occurring again, that you rebuild your clustered index with the fill factor. Means now, again, with a fragmentation of almost 0%, 1,500 pages and the fill factor of 50%. Now again, you can insert records. Let's make 10,000 as previously. Now you can insert again records and you have no page splits. Make sense? Okay. And as I've said previously, forget about the performance counter. Of course, when you're just inserting into one table, it's easy to see if you have page splits. But when you insert into a table with an ever-increasing clustered key value, for example, let's do the following. Let's create a table foo. Let's create a call one int identity 11 primary key. And insert into foo. I think it's default values. Yeah, and let's run that very, very often. You still have page splits. Good ones. Just think about that. Use less information. Okay? Because you have no idea if those page splits are occurring at the very end of your clustered index or somewhere in the middle because you are using a random clustered key value like a unique identifier. Okay? So you should not always trust SQL Server. So fill factor, the first option how we can deal with that problem. Second option, we can enforce our primary key constraint with a unique non-clustered index. I create here a database, and the easiest thing that you can do on earth when you work with a unique identifier, you create a primary key and enforce the primary key constraint with a non-clustered index, with a unique non-clustered index. That's the easiest way to deal with that problem. By default, SQL Server enforces the primary key with a clustered index. It's the default option, means you don't need to specify it, and nobody knows that you can also enforce the primary key with a non-clustered index. Means in that case, you have your index fragmentation in the non-clustered index. But nobody cares about that index fragmentation because you can afterwards cluster and physically pre-sort your table on a different column. For example, let's create a clustered index on column, let's say first name and last name, or last name and first name, like a phone book. Okay? Just think about that. We can still work without any problems with unique identifier values as primary key constraints, as long as we are enforcing the primary key constraint as a non-clustered index. In that case, when we look now to sys indexes, you can see we have two indexes. We have our non-clustered index, which is a unique one and enforces our primary key constraint that we have created here. And we have our clustered index that we have created in the second step. So in that case, we have physically pre-sorted our table on last name and first name. Means when you just insert at the very end of that table, which is with last name, first name not really the case. But when you insert, like with an int identity at the very end, you have no problems. Because your index fragmentation only happens in the non-clustered index. And the non-clustered index is just a supporting non-clustered index to enforce the uniqueness in your primary key column. Normally, you will not read from the leaf level of the non-clustered index. So you don't care about that fragmentation. So that's the simplest way how to work with unique identifier values. Just enforce them as a unique non-clustered index and all your problems are just gone. Very simple. Of course, when you have an existing database, an existing table, it's much harder. So let's drop that one. And again, let's create our bad table. Let's create that bad table. Let's insert 10,000 records, means we have again page splits and everything. And now we want to enforce at a later point in time the primary key constraint with a unique non-clustered index. As I've already said, we have to drop our foreign key constraints. If you don't trust your application, maybe it violates the referential integrity, you have to set your database to single user mode so that nothing else can do a work in that database in the meantime. Let's copy out the name of our clustered key before we set the database to single user mode. Then you have to disable all your foreign keys, means you have no referential integrity anymore. And then we drop our old primary key constraint. So we have now no primary key constraint anymore on that table. Now it depends. Maybe you have already a column with an ever increasing value on which you want to add your clustered key later. Maybe you have an order date column, and order date also gives you an ever increasing value. You will mainly make orders in the future and not in the past. If you don't have an ever increasing column, add one, like an int identity column like here. So when we look now into that table, you can see we have our unique identifier column and we have our ever increasing clustered key column that we have added in that example. Means in the next step, we create our unique clustered index on that column that we have added previously. Doesn't matter, it's an ever increasing column. And finally, we add back the primary key constraint on the original unique identifier column, but now we enforce the primary key constraint with a unique non-clustered index. So from an application perspective, nothing has changed. You still have your primary key constraint on the same column, but you're enforcing it now with a unique non-clustered index instead of a unique clustered index. Then you can again enable all your foreign key constraints, means you have again referential integrity and you bring your database online. When we look now on the statistics of our indexes, you can see now Our clustered index has currently no fragmentation. Our non-clustered index has currently no fragmentation. And now let's insert 10,000 rows into that table. When we now look on the fragmentation again, you can see our clustered index, which is our table data, has no index fragmentation, almost nothing, because we just added the very end of the clustered index. There are no page splits in the clustered index. But of course, the non-clustered index, which enforces now our primary key constraint, has nearly again a fragmentation of 100%. But who cares about that fragmentation? No one. Because you are not using that non-clustered index. It's just a supporting non-clustered index to enforce the uniqueness in your primary key constraint column. Nothing more. Means you just got rid of your index fragmentation in your clustered index. And the clustered index is your table data. Make sense? So various ways how to deal with that problem. The easiest one, when you create your table, enforce the primary key constraint immediately with a non-clustered index. If you have already applications in production, you can do it the hard way, like here. Normally, you will not go that route because it's just too complicated. So mainly people are just playing around and working with the fill factor to lower down your page splits. So you have some way to get that problem under your control. Questions so far?
I have one question. Why did we create a non-clustered index at all? I mean, it's really to help enforcing.
Because we want to have the primary key constraint. When you have no primary key constraint, you can't create for when key constraints, means you have no referential integrity. And every record in a table should be unique.
Yeah.
The set theory itself, on which the relational model is based, on which our databases are based, the first principle is of the set theory, as I've said on Monday, records are unique. Means when you have no primary key constraint, you are already violating one of the basic principles of the set theory. Yeah?
Why doesn't Microsoft then set the primary unique key to have a non-clustered index rather than clustered?
No idea.
Yeah.
No idea.
That's another
It's
question.
Microsoft.
That would make it too easy.
Yeah. It would be just too easy for us.
It looks like we're done.
Every primary key constraint is indexed by default with a unique clustered index, as we have seen. Every foreign key constraint has no index. Just think about that. Means when you're restricting on a foreign key column, you make no seek, because you have by default no supporting index on that column.
Yeah, but if you can have many foreign keys in one table, you cannot index it on all foreign keys. It will make it slower rather than faster.
Depends on your workload.
Yeah.
As I've said in the morning, the problem with indexing is, on one hand you're improving your read performance, on the other hand you're degrading your write performance. So
Yeah.
you have to analyze your workload and you have to find those queries which are crying for a missing index. Of course, it doesn't make sense to index every possible query, but the most important ones need an index. And every foreign key column is just unindexed by default. So that's also some crazy thing in SQL Server. With a primary key constraint, we get an index, sometimes a good one, sometimes a bad one, depending on the data type. With a foreign key constraint, we have no index. Oops. Okay. Now we have seen all the disadvantages. The great thing about unique identifier values is that they are scaling very, very well. When you have an ever-increasing value, like an int identity column that we had here, you have no throughput when you're working with multiple users. Just think about that. The problem is called the last page insert latch contention. When we inserting rows at the very end of our clustered key column, of our clustered index, then you generate at the very end of your clustered index a single hotspot, because all your records are just inserted at the last page. Makes sense. 1 comes for 2, for 3, for 4, for 5, for 6, for 7, for 8. When SQL Server changes a page in memory, for example, when we add a record to that page in memory, SQL Server has to lock that page in memory with a so-called latch. Means, when you make an insert on that page, nobody else can read that page in the same time, and nobody else can write to that page at the same time. Means, your inserts at the very end of your clustered index are mainly single-threaded. One query after the next one. Means you have no throughput. Imagine, for example, you have tables like logging tables, auditing tables, where you have to insert a huge amount of rows with the least amount of time. In that case, an ever-increasing clustered key value like an int identity column doesn't really scale. Just think about that. We have, again, multiple ways how to deal with that specific problem. The easiest way is to spread your inserts across the whole leaf level of the clustered index. How can we spread the inserts across the whole leaf level of the clustered index? We use a random clustered key value like a unique identifier. Just think about that. You can use the unique identifier value to improve the throughput of your application. Previously, we have said the unique identifier value is a crazy idea because it degrades the throughput. Now we are saying the opposite one. There are also other ways like hash partitioning when you're using the enterprise edition of SQL Server. Even in memory OLTP, which was introduced with SQL Server 2014, can help you with that problem. But now I just want to show you the approach with the unique identifier value, because then you think the world is just crazy. I create here now a perfect table, which doesn't scale, with an int identity column, and we enforce our primary key constraint with a clustered index, which is just the default. So just the best practice. I create a simple stored procedure which inserts in a while loop 10,000 records. And now we want to stress test that stored procedure. You can download for free from Microsoft the so-called RML utilities. It's a free download, doesn't cost you anything, and within those tool set you have one tool called ostress.exe, and with that tool you can make a stress testing. What I'm doing here is the following. I'm connecting to my SQL Server instance, and I'm specifying the stored procedure that I want to execute. Or you can also specify a query that you want to execute, and you specify the number of users. In my case, I want to execute that stored procedure with 100 parallel users. Means 100 parallel users are trying to insert records at the very end of your clustered index. One session after the next one. Just think about that. So let's go to the command line and run that. Takes a few seconds until the users are connected to SQL Server. And when we go to Activity Monitor, you can see now immediately that we have almost 100 waiting tasks. We're running with 100 parallel users, and mainly one user is performing work. All the others are waiting, because SQL Server locks those pages in memory. Means nobody else, when you make an insert, nobody else can read from that page in the meantime, nobody else can write to that page in the meantime. That's the so-called last page insert latch contention. You can also see that very easy from system exec requests. Every query has a status. Running is great, suspended is bad, because suspended means you're not doing any work, you're waiting on something. As you can see, almost every query is in the suspended state, and we are waiting on a page latch exclusive. Means we are waiting on that latch in memory. We are waiting until we can change that page in memory. Just think about that. You are waiting on in memory. Takes now some time, around 1.5 minutes, and then we have inserted those rows into that table. 1.5 minutes. When we count those rows, I'm not fooling you here in any way, we have inserted 1 million of rows in 1.5 minutes. And now we do the following. We create a bad table. Nice thing, we also have those tables already in production. We use a unique identifier as a cluster, as a primary key value. Means we are distributing our inserts across the leaf level. Means we have concurrency when we insert those records, because SQL Server latches individual pages at the same point in time. We just improve concurrency. Again, I create the stored procedure. Now we generate our primary key value with new ID. And again, I'm calling that stored procedure with 100 parallel users. Around 6 seconds. Just think about that. I haven't fooled you here in any way. We still have 1 million of records in that table. Nice, isn't it?
Sometimes for reading it's even more dramatic. One of our DBAs made not similar but the same thing.
Yeah.
Because we had the same problem. And
Yeah.
we had like 4 million, or no, at this time we had 13.5 million records.
Mm-hmm.
So a simple query with like where on one column was taking like 12 minutes. After that, it was taking 4 seconds,
Yeah.
or 3 seconds, or something.
Of course, with that approach, again, we have all the various problems that we have already talked earlier. We have just improved the throughput, the concurrency of one specific query. Of course, it doesn't mean now that you are going back to your databases and you say, hey, cool, we have here int identity, let's swap that and create a unique identifier value. No. It only makes sense when you have that specific problem. You don't have that problem on your orders table. If you have that problem on your orders table, congratulations, then you have a very, very good company. But just think back, as I have said previously, logging auditing tables, where you have to insert in a very, very short time a huge amount of records. then it's very easy, as you have seen, to hit that specific problem. And then, very simple, you can work with a unique identifier value to distribute those inserts. Of course, index fragmentation 100%, page splits, random I/O, a large lookup value in your non-clustered indexes. Same problems that we have already seen previously. So as you have already seen now, unique identifier as a primary key value, normally not really a good idea when you enforce the primary key constraint with a clustered index. When you enforce it with a non-clustered index, all your problems are gone, and it can also help you when you have that specific last page insert latch convention. Cool. We are at the end. How do you have enjoyed the session? Lot of things. If you want to know more about SQL Server, performance tuning and troubleshooting, I'm coming back in the first week of June where I'm running my SQL Server performance tuning workshop. It's a workshop 5 days entirely about performance tuning and troubleshooting on SQL Server. You will find more information about the workshop on my website, sqlpassion.ad, and if you give me a business card of yours, I can also give you a discount of 10%. Okay, when there are no more questions, as I thank you for attending my session, I have also tomorrow 2 more sessions about deadlocks tomorrow morning, wow, and another one after lunch about joins in SQL Server. Okay, thank you.
I had a question about so Microsoft, have they introduced something called new sequential ID to help?
Yeah, new sequential ID provides you sequential unique identifier values.
Is that to
It can also help you. But I had already seen some customers which were able, in a very large scenario, to generate duplicate values across multiple sessions, which is also not so good when you have your primary key constraint on that
But
card.
it's definitely better than using GUID, isn't it? Just a new GUID. It's just randomly generated. That's at least sequential.
Yeah, sequentially random generated. Normally I prefer new ID because I want to have a unique value. So I'm not really a big fan of new sequential ID.
I just
Yeah.
asked that because
Yeah.
I think we use entity framework, so
Mhm.
by default, I think the
Yeah.
later version it sets the value to be
Okay.
a new sequential GUID.
But it can be also an option to eliminate page speeds, of course, because you're just generating a sequential GUID value, which is hopefully still unique. Hopefully. As I've said, I have already dealt with a few specific customers in a large-scale environment where they were able to generate duplicate key values. Okay, so thanks for attending, enjoy the evening, and let's see hopefully tomorrow morning. Thanks.